Okay, hello everyone. My name is Michael. I'm from the Max Planck Institute for Astronomy in Heidelberg, Germany. I'm a PhD student there. And I was very intrigued by the talks of the previous speakers, especially Sergei's and Eduard's talks about the different mechanisms for outburst triggers. And in this talk, I'm going to focus on one specific one that they already mentioned, which is the MRI triggered outburst. So in general, I'm working together with my supervisor, Mario Flock, on the stability or instability of the inner disk regions. So the regions we are interested in can be seen in this plot here. So we're starting at about 0.05 astronomical units, going out to about 10 AU. And we do this in the context of two-dimensional radiation hydrodynamic simulations in an axisymmetric fashion. And we resolve the vertical structure of the inner disk. So I'm going to mention in a minute what we're actually seeing here, but for now, this disk structure that we see here was derived from hydrostatic models, for example, by Mario and his colleagues in 2019. And the first task of our new project was to take this as an initial condition and evolve it in time hydrodynamically to see if it is stable over long periods of time. And as you can imagine, since I'm giving this talk here at this conference, it will not be stable. So let's have a look at what we're actually simulating here. So our disk is irradiated by a solar-like central star, and the radiation is reprocessed by the disk material using a radiation transport description. In this context, of course, dust plays an important role because the dust is the main contributor to the opacity of the disk material. We have a description for dust sublimation in our models. So here I plot on this green line the dust sublimation front, the dust sublimation temperature. So in practice, this means we have a upper limit of the dust to gas mass ratio of 10 to the minus 3 in the outer cooler regions of the disk. And this value decreases towards 0 as it crosses the dust sublimation temperature, which is also dependent on density. So we basically have an almost purely gaseous disk in here and a gas-dust mixture out here. When thinking about hydrodynamics, we also have to think about the transport of angular momentum, and we do this by including turbulence in our models. We describe the turbulence in terms of viscosity, where we use the typical Shakura-Sanyaev alpha description. So similar to before, we have a low value of alpha out here in the cooler regions in the dead zone, so it's not 0, but it has a lower value of 10 to the minus 3, and this value smoothly increases over the MRI activation temperature towards a maximum value of 0.1 close to the star. So we assume that at the temperature of around 900 Kelvin, the disk is ionized enough to allow the occurrence of MRI, which produces this MRI activation front represented here by this black contour line. And when talking about viscosity, we also have to take into account the heating that's produced by the viscous dissipation. So as the title already said, we expect to see instability developing in here, producing an accretion outburst. So the first question we need to ask is, how can this structure become unstable? And then what actually happens to the inner disk during and after the instability? So to tackle the first question, we can think about it theoretically for a moment. So we have a mismatch in mass transport rate between the outer and the inner disk because the turbulence is very different, which means for the material that is located somewhere around here, so just outside the MRI activation temperature in the inner region of the dead zone, that it will receive a lot of angular momentum coming out from the inner disk, but it cannot give it off at the same rate because the turbulence out here is smaller. That means that the material in here will be, or the radial mass flux of the material will be slowed down, which leads to a buildup of density in this region. And the buildup of density has two important consequences. One is that the optical thickness of this region will become larger, which means that the heat that is produced in there cannot be transported away as efficiently. And on the other hand, the viscous heating is enhanced in the high density region. So as a consequence, the temperature will increase in this region around here. And eventually, the temperature can reach the MRI activation temperature or get into the vicinity of the MRI activation temperature. And then the alpha value becomes strongly dependent on the temperature. The MRI gets active, and a runaway heating effect is launched in this region right here, which causes the instability. we can have a look at the evolution of the instability when looking at a few time snapshots. So we have here 5 snapshots in time during the instability evolution. On the upper row, we again have the 2D temperature maps, and on the lower row, the corresponding surface density in blue. So the first column here shows the onset of the instability. So if you remember that the black contour line is the MRI activation temperature, there's a small region here where the MRI becomes active, causing this runaway heating effect and inflating the MRI active region into this toroidal shape that we see here. Within this region now, the disk is highly turbulent, which means that all the mass that was stored in there, in the inner regions of the dead zone, becomes highly turbulent and is dumped onto the star, which causes the accretion outburst. When looking down here on the, to the surface density evolution, we can think of the expansion of this MRI active region as the propagation of a heating front through the disk structure. And I've overplotted here something that was also mentioned in Lee's talk, for example, a critical surface density value below which the MRI can no longer be sustained. And this is important in this context because this determines how far the heating front can propagate outwards. A heating front will always push in front of it a spike in density, which we can see here. So the heating front in this case is equivalent to the black contour line here, so the MRI activation front. And as soon as the density behind the heating front, which will be this valley here, as soon as this valley goes below the critical surface density, the heating front will stop and will get reflected into a cooling front, which runs back towards the star slowly, shutting down the MRI activity and reinstating the disk structure as it was before, or approximately as it was before. But as it turns out, this is not the end of the story, at least not in our simulations, because this process reflares a few times. And each reflare follows the same procedure as the first ignition does. So a heating front launched outwards is reflected into a cooling front, comes back, and this happens a few times. But each time the reflare is less or has a smaller amplitude than the previous one because there's just less mass available to be made MRI active. So, and after a few reflares have occurred, the disk enters the quiescent phase again. And each reflare or each outward propagation of the heating front places one such density spike in the surface density distribution. So we end up in the end after the instability with this sawtooth-like shape. We can have another look at the instability or the surface density evolution during the instability in a space-time plot such as this one. So we have the radius on the x-axis and the time on the y-axis. Within the shown time frame, there are 2 such instability cycles developing, one at the very beginning and one after about 2,500 years. And the surface density is color-coded here. So something that we can see, for example, is that after such an instability cycles, such a cycle, the density in here is reduced, so the mass has drained onto the star and is slowly getting refilled during the quiescent stage by an influx of material from the outer disk until a new instability cycle can be launched. The white contour lines here represent the locations of pressure bumps in the inner disk structure. And pressure bumps are always interesting to look at in protoplanetary disks because they are generally capable of trapping solid material within them and allowing the growth of the material to larger objects, or maybe even induce streaming instability and enabling the efficient production of planetesimals. So we can have a closer look at one of those instability cycles to get a few more details. There is one very prominent pressure bump here during the quiescent phase, which is exactly at the position where the density slowly builds up during the quiescent phase and where the MRI then gets activated. And as you can see here, so this stable pressure bump is down here. This one gets destroyed by the evolution of the instability. And I've overplotted here also the location of the inner edge of the dead zone, which is basically the MRI activation front, traveling outwards and backwards. And whenever the MRI activation front reaches its outermost extent, a pressure bump is placed in the density structure of the disk. So each reflare places one such pressure bump in the disk structure. Now, the big question is, are those pressure bumps strong enough and do they stick around long enough to be able to trap enough solid materials within them and maybe induce streaming instability to form planetesimals efficiently? And there are a few things to consider here. For example, we see here that those pressure bumps diffuse away relatively quickly on the viscous timescale. But this is a consequence of our chosen alpha parameter in the dead zone, which is chosen to be relatively high. So if the turbulence would be lower, those pressure bumps would stick around longer. But even with this strong turbulence in the dead zone that we assume, the first approximate calculations point to the possibility that they are in fact strong enough and stick around long enough to at least induce streaming instability. But of course, to confirm that, we have to do dedicated simulations for that. It also turns out to be quite useful to analyze the disk structure in terms of its thermal stability or thermal equilibria. So we have seen a plot such as this one a few times before in Sergei's talk and in Eduard's talk. And we can draw a similar S-shaped curve in this MRI activation scenario. So we have, again, two stable branches of thermal equilibria, a lower and an upper branch. And when talking about the high state equilibrium, what I mean is the stage of the disk on the upper branch of the S-curve, which is realized in this region where the MRI has become active around the midplane. And maybe you've heard that very recently it became legal in Germany to be in a high state. So I thought it would be worthwhile to check out, but only in a scientific sense, of course. So what we can say, for example, is that in here, in the high state equilibrium, the dust already begins to evaporate, which is shown here by this green contour line, which is the dust evaporation temperature. Which means that as the dust evaporates, the optical thickness of this region becomes smaller, which means that the cooling efficiency increases. So the dust will evaporate up to the point where the cooling rate can counter the enhanced heating rate, which is produced by the viscous dissipation. And at this point, when the cooling rate is approximately equal to the heating rate, then this upper stable branch of the S-curve is realized. So, and we can ask the question, oh, by the way, of course, the lower branch of the S-curve is realized in the regions where the MRI is completely inactive. We can ask the question, well, what is the dust content in the high state equilibrium that produces the equilibrial state? And we can do a few fits to our models, and what we can see is that we can describe the surface density of the dust as a function of the radius and the surface density of the gas. But of course, we have to be very careful with this, because this is a consequence of the chosen parameters for our simulation. So if we change, for example, the alpha description or the opacity description, then this formula would change as well. So we have to take this with a grain of salt. Okay, this leads me already to the summary of what I wanted to talk about. So we have seen that a turbulence transition in the inner disk can lead to the development of the instability through MRI activation, which causes the episodic accretion event and inflates the MRI active region into a torus-like shape. In our simulations, reflares seem to be a consistent outcome, so we can't really seem to get rid of them as for now. Pressure bumps are created and destroyed by the instabilities, so usually those who are stable throughout the quiescent phase are destroyed, and there are new ones created, and those that are newly created may be capable of inducing streaming instability and allowing the efficient formation of planetesimals. And at the end, we have seen that the dust evaporation plays an important role in establishing the thermal equilibrium in the high state of the disk. It is also worth mentioning that, of course, there are a lot of things that we do not consider in our models as of now. For example, we chose our disk masses so that they are gravitationally stable, so we have no gravitational instability occurring in our models. Also, as has been mentioned a few times before, we should couple the description of the turbulence of the alpha more carefully to the non-ideal magnetohydrodynamic effects, which we can do and hopefully will do in the future. There are other magnetohydrodynamic effects that we do not consider, for example, the outflow of winds, of magnetically drilled winds, or the interaction with the stellar magnetic field. we also do not yet consider explicitly the evolution and drift of dust, which will be part of a future step, of course. And of course, we have to go into the direction eventually of producing light curves and synthetic observations as soon as we are confident enough in our results to be able to compare them more directly to observed accretion outbursts. Okay, that's it for me for now. Thank you for your attention and go ahead with your questions.
Do you have any questions? Oh, we can answer questions. Yeah.
Nice. Thank you. Very interesting talk. A few questions. So I'm working on dust a lot, so I have a lot of dust question for you. So you said that you don't include the drift. So how do you have the replenishment of this accumulation of dust in the inner regions? How do you get it? So you mentioned that you have this instability every 2,500 years because the dust is coming back, right, and reaccumulating. So how do you get this without drift?
Yeah. So what we are simulating is the gas evolution, essentially. And we say that the dust is a fraction of the gas described with the dust to gas mass ratio description. And the dust to gas mass ratio varies according to the temperature or according to our dust sublimation description. So we do not include the dust as a separate fluid or as particles, just as a part of gas. And what I mean by the influx of material towards the inner disk to refill the inner disk, I mean the influx of gas carrying along with it the dust.
And what particle size do you assume? So I guess you need to assume particle size to calculate the opacities and so on.
Yeah, yeah. So we assume a range of, I think, 0.005 to 10 micron, something like that, for the opacities.
Thank you.
Hello, thanks for the very interesting talk. Actually, so many MRI simulations show that the alpha over turbulent velocity depends on vertical direction. It increases from the midplane to the disk surface. So is your alpha in the dead zone also varying with the vertical direction to realize the fact, or you just assume alpha constant along the vertical direction?
Yeah, so for now, we assume that alpha is constant and only depends on the temperature. So it does not depend on the vertical placement. But I know of such descriptions, of course, and we are currently in the process of including that, the vertical dependence of the alpha, to see if it changes. And it's going to be very interesting to see. Yeah.
Thank you so much.
Well, this is more of a comment rather than a question. I think both you and Edward are completely right to worry about this, and I worry about what dust really does in these disks. So it's really great that that there's some work in that direction, and it's of course very hard to include all the physics in there. But yeah, we have to start somewhere, so that's exactly fantastic. Maybe this is one of the things that I haven't yet considered in my models, and maybe that's what helps to explain why these outbursts propagate farther into the disk than just the hydrogen thermal ionization, would, and would give you longer outbursts. So great.
Thank you so much.
Do you have inflow from your outer boundary, or is that just fixed? And does it matter? Is it too slow?
So no, we have only a fixed boundary which does not allow inflow of material now. But Yeah, exactly. It does not really matter because it won't arrive at the inner disk in the time frame that we can simulate.